In this section, we're going to talk about the enthalpy that comes from bond energy. So let's just first talk about what bond energy is, okay? There's this common misconception that energy is released when bonds are broken. So we break bonds and we just, explode all this energy out. But this is mainly false. The contrary, honestly, is true. In order to break bonds, we have to put energy in to break the atoms, to separate them. And then when those atoms rearrange and form something new in the course of a chemical reaction, when bonds are formed, energy is released. So, as an example, energy is required to break the methane bonds in the combustion reaction that you see in the gas burner, and the energy is released when the products are formed, when water and carbon dioxide is formed, which it's released in the form of the heat energy that we get from the flame. So that energy is released in the form of heat. That's how we heat up our pots and pans on the stove. So the big takeaway here is what we see in capital and bold letters up at the top. Energy is required to break bonds. So we input energy to break bonds, and energy is released when bonds are formed. So when you think of your chemical reaction going from reactants to products, to break your reactants apart, you have to put energy in. And when those atoms rearrange and form the products, energy is released. If we are given bond energy values, we can calculate the enthalpy of a reaction just using those bond energies. The difference in the energy consumed during bond breaking and the energy released during bond formation is what the net change in energy, which we usually call the enthalpy of the reaction. Since the bonds are broken first within the reactants, prior to bonds formed in the products, we can use the following equation for finding the enthalpy change from standard enthalpies of formation as follows. The overall, so on the left, this delta H0, this is the enthalpy for the overall reaction. It's the sum of all of the reactant bond energies minus the sum of all of the product bond energies. You have to subtract the total product bond energies from the total reactant bond energies. Remember that for the reactants, we're putting energy in. For the products, that energy is being released. Okay, that's why we have a negative or subtraction here. The sum of the bond energies for the reactants is always positive. Why? Because breaking bonds requires energy, so it's always endothermic. The sum of the bond energies for the products is always negative because forming bonds always involves a release of energy, or it's exothermic. This negative sign right here, this subtraction here, is already supplied in the equation, so we're accounting for that in the equation. Whether the enthalpy for the overall reaction, so this total right here, whether the overall reaction is endothermic or exothermic depends on which of these is larger. Does it take more energy to break the bonds apart than is released when they reform? Or does reforming the products, rearranging the atoms for the products, release more energy than is required to break the original bonds? Okay, so it depends on which of these is larger to tell us, will the reaction be overall endothermic or exothermic? Throughout the next several slides, we're going to walk through this example together for bond energy. Find the enthalpy of the reaction for the combustion of 1 mole of methane given the bond energies in the table. So we have a carbon-hydrogen single bond, oxygen-hydrogen single bond, carbon-oxygen double bond, and oxygen-oxygen double bond, okay? And If you haven't tried this on your own or with your group yet, try it first, and then in the next several slides, I will go over how to do it with you. Okay, so here's our question again. The first thing we need to do is figure out what are our reactants and what are our products. We need to write a reaction. So we're told that it's combustion of 1 mole of methane. Okay, so first things first, write an equation making sure that the coefficient in front of the methane is 1 because we're combusting 1 mole of methane. So combustion, remember, is a reaction of the hydrocarbon, the methane in this case, CH4, with oxygen. And the products for combustion reaction are water and carbon dioxide, so H2O and CO2. And then I've just balanced it. So in order to do that, we have 4 hydrogens on the left, so we need 2 water molecules, and that gives us 4 oxygens on the product side, so we need to balance the oxygens on the reactant side. So our coefficients are 1, 2, 2, 1 in this case. Now, we have a balanced reaction, but we don't know how are all of these bonds arranged, right? So like how are the bonds broken? What do they look like when they're broken, and how do they look when they're reformed? So the next thing I did was I drew Lewis structures for each of the reactants and each of the products. So methane, carbon in the middle, 4 single hydrogen bonds. We have 2 oxygen molecules, which is O double bond O, produces 2 water molecules and 1 CO2, okay? Why do we do that? Well, remember, we have these individual bond enthalpies. And so we're going to break every one of these bonds and 2 of these, and we're going to reform these bonds on the right-hand side. So we need to know what are those bonds that we are breaking and reforming in order to find the enthalpy for this reaction. All right, now that we have these Lewis structures, we can interpret them to see how many bonds are we breaking and how many bonds are we forming, okay? And what are the bond enthalpies associated with that? So if I look at these carbon-hydrogen bonds, there are 4 of them, right? We're breaking 4 carbon-hydrogen bonds. So we take the bond enthalpy for a single carbon-hydrogen bond and we multiply it by 4. That's how much energy we'd have to put in to break all 4 of those bonds. Similarly, for the oxygen molecules, it's an oxygen-oxygen double bond that we're breaking, but we have 2 of them. So we're going to break an oxygen-oxygen bond 2 times. So if we take this oxygen double bond oxygen and we multiply it by 2, that's the total energy we have to put in to break those 2 double bonds. Now, remember that when the atoms rearrange to form the products, energy is released. So now we find out how much energy is released. Well, energy is released to form these oxygen-hydrogen single bonds. There are 2 of them in 1 molecule, but we have 2 molecules. So that's 4 bonds forming total, right? 4 oxygen-hydrogen bonds forming overall. So we want to multiply that by 4 to find out the total amount of energy released in the formation of those bonds. And similarly, we have 1 carbon dioxide molecule that forms, and when it does, it forms 2 carbon-oxygen double bonds. So we can take this bond enthalpy associated with the carbon-oxygen double bond and multiply it by 2. I'll show you the math on the next slide, but this is how we interpret these Lewis diagrams to help us determine how much energy is required for each bond to be broken on the reactant side and for each bond to be formed on the product side. Okay, so what I did was I took our number of bonds from the previous slide, and I just substituted them into our equation for the enthalpy of the reaction. So the sum of the reactant bond energy. So our reactants are methane and oxygen. So 4 carbon-hydrogen single bonds plus 2 oxygen-oxygen double bonds, right? Then minus the sum of the product bond energies. So we determined that there were 4 oxygen-hydrogen single bonds plus 2 carbon-oxygen double bonds. And from there, we can just substitute the values from the table that are given. Okay, so 4 times 413 plus 2 times 495 minus 4 times 463 plus 2 times 799. We get an overall negative 808 kilojoules per mole. So that means overall, the energy released from the products is greater than the energy required to put in to the reactants. And that's a good thing for a combustion reaction. Like in this example, the methane gas to heat the stove, right? That's important. That energy released can be released as heat, and we can use that energy to cook our food or heat our home or, you know, run the engine in our car, whatever combustion reaction you want to think of as your example there.